Have you ever seen a movie where someone throws a lit match into a puddle of gasoline and whoosh, the whole puddle instantly erupts in flames? It looks incredibly dramatic, doesn't it? Well, I'm here to tell you that what you're seeing is a classic Hollywood exaggeration. Many people believe that the liquid fuel itself is what's burning. It seems logical, right? You pour the liquid, you light the liquid burns. But science, you see, has a fascinating twist to this story. The truth is a little more complex, a little more invisible, and a whole lot cooler. The liquid isn't the star of the show, it's just setting the stage for the real performance. Let's consider this. Fire is a chemical reaction, and like any good recipe, it needs specific ingredients. We often talk about the fire triangle: fuel, heat, oxygen. You can have a big pile of wood, fuel, sitting there forever, but it won't magically catch fire. You need to add heat, like from a match or a lightning strike. But even with fuel and heat, you're still missing one crucial component: oxygen. Without oxygen, there's no fire. It's the invisible gas all around us, about 21% of our atmosphere. That allows the reaction. Now, think about a dense liquid, like gasoline, diesel fuel. In a liquid, molecules are packed closely together. There's no space for oxygen to mix deeply. The real fuel for the fire isn't the liquid you see, but the vapor you don't. All liquids have a tendency to evaporate, meaning some molecules gain enough energy to leave the surface and become a gas. We call this gas a vapor. Think about a puddle drying in the sun. That's evaporation in action. The same thing happens with flammable liquids like gasoline. Tiny, invisible fuel molecules leap off the surface and float into the air. These vapors are the true fuel the fire consumes. The liquid is just the reservoir supplying the vapors. Unlike dense liquid, vapors are free-spirited. As a gas, their molecules are spread far apart and move rapidly, leaving plenty of empty space. Fuel vapors rise from the liquid, then mix thoroughly with oxygen molecules in the air. You get a combustible cocktail just waiting for a spark. This vapor-air mixture is what's flammable. Without it, a lit match over liquid often does nothing. There's not enough oxygen at the ignition point. Liquid fuel molecules, little red balls. Oxygen molecules, little blue balls. Some reds gain energy, jump out, and now reds and blues dance together. A bit of heat, an ignition source, starts the party. Heat provides activation energy. Bam! A chain reaction starts, and you get fire. Next time in a movie, remember, the flame races through the vapor cloud above, not through the bulk liquid. So, if vapors are the key, does that mean all flammable liquids are equally dangerous all the time? Not at all. This brings us to a super important concept in fire science called the flash point. In simple terms, the flash point is the lowest temperature at which a liquid gives off enough vapor to form an ignitable mixture with the air. It's not when the liquid automatically catches fire. You still need a spark. Below its flash point, a liquid doesn't evaporate fast enough to make an ignitable vapor cloud. Let's use two common fuels, gasoline and diesel. Gasoline, diesel. Gasoline has a very, very low flash point, around -40 degrees Celsius, or -40 degrees Fahrenheit. Even on the coldest winter day, gasoline produces enough flammable vapor to ignite if a spark is introduced. This is why gasoline is extremely volatile and dangerous. Its vapors are almost always present, just waiting for an ignition source. You don't need to heat gasoline to make it dangerous. Everyday temps are far above its flash point. Now, let's look at diesel fuel. Diesel has a much higher flash point, typically above 52 degrees Celsius, or 126 degrees Fahrenheit. At 20 degrees Celsius, a puddle of diesel isn't producing enough vapor to ignite. Toss a lit match into room temperature diesel and it likely goes out with a sizzle. To burn diesel, you must heat it past its flash point first. This difference in flash point is everything when it comes to safety. Now we can see why safety regulations are based on hard science, not just on what looks flammable. A clear liquid like gasoline and an oily liquid like diesel behave very differently because of their flash points. Regulators, firefighters, safety engineers don't just guess. They use the flash point to classify liquids and create rules for how they must be stored and handled. A substance with a very low flash point, like gasoline, requires much stricter containment, ventilation, and ignition control measures. A substance with a high flash point like diesel or motor oil needs less stringent controls. This scientific understanding helps bust myths and prevents accidents. People might think any fuel is explosive. That's not true. The danger comes from the invisible, flammable vapor-air mixture. That's why you're told not to use your cell phone while pumping gas. Not because the phone ignites the liquid, but because any small spark could ignite dense gasoline vapors. The rules control ignition sources where flammable vapors exist. Think about safety at home. Cooking oil is flammable, but it won't explode on your counter. Its flash point is high, usually over 200 Celsius or 400 Fahrenheit. Heat it past its flash point and then its auto-ignition temperature, and it can catch fire. Big idea. Liquids don't burn, vapors do. A fire needs fuel vapor, oxygen, and heat. The flash point shows how easily vapor forms. This is the basis of modern fire safety. It helps us build safer cars, transport fuel, and prevent accidents.